The next talk is by Dr. Zitong Yu, entitled Facial Video-Based Physiological Signal Measurement, Recent Advances and Effective Applications. Please take it away.
Okay, thank you, Alice. Okay. Hi, everyone. I'm Zitong from University of Oulu. Today, I present two related papers about a physiological measurement from face video. One is accepted by IEEE Signal Processing magazine last year. One is by IEEE Signal Processing letter 2 years ago. At the beginning, I will introduce the facial video-based physiological measurement, recent advances and effective applications, so that everyone can know the background of the physiological measurement. In the traditional way, we usually measure our physiological parameter, for example, our heart rate and our breath rate from some contact sensor, for example, the ECG sensor or our wearable glasses. But with recently the computer vision technique and machine learning technique development, remote heart rate measurement become hotter and hotter. So you can imagine that we have a video conference now, but some parameters can measurement continuously from our video screen directly. What is rPPG technique? As you can see in the pipeline, rPPG signal can be extracted from the facial sequence by analyzing the skin color trends caused by periodic cardiac heartbeats. The classical pipeline is that we will first do some facial video pre-processing, for example, face detection or facial skin segmentation. After that, we will extract a single, for example, RGB signal from this face region or some partial RI region of interest. And after that, we extract this core signal. We will use some signal processing method, for example, some filtering technique or some time frequency analyzing to get our target parameter estimation. And after that, we can apply these signals and parameter to further effective application, for example, emotion recognition and stress estimation. Here is a demo to show how the color comes from the face with color magnification. As you can see, after the color magnification, you can see the red and the green color. They will change periodically from the face region. And if we detect the RI region from the face like this, and we can easily average the intensity value within the RI region and get the discontinuous signal. Here we call it rPPG signal. And some approach for rPPG measurement can be summarized into this table. There are three-stage rPPG measurement. At first, we usually do some video pre-processing, for example, face detection, RI selection, and after that, maybe we will do some RI tracking or some signal map representation or some video enhancement. After pre-processing, we will like to recover the rPPG signal from this pre-processed face or map or video. For example, some traditional unsupervised method maybe use some signal processing method or some deep learning neural network to predict the signal. After that, we will also do some post-processing to refine the signal and get our target parameters. Here I show some two very classical RI selection method. For this one, they assume that the RI region around the cheeks and the forehead, they have stronger rPPG cues. So usually they will first define this RI region and use some RI tracking strategy across the whole video to ensure the rPPG signal can always measure within these signals. And another strategy is do the whole face skin segmentation to get each skin pixel for each frame. And after that, rPPG signal can be calculated within all these skin pixels. Another representation is that we can define many dense RI region, small RI region, and each RI region we can get rPPG signal from RI region. And after that, we have RI regions. We can generate a ST map like this. The two dimension is the RI numbers and the time sequence frame numbers. So usually they will use this kind of input for the subsequent rPPG recovery. After that, I will introduce two classical end-to-end supervised rPPG signal recovery methods. One is the first end-to-end method in ECCV 2018. In this paper, they first calculate the normalized difference frame from continuous two frames. They assume that the color change will be very subtle. So after they calculate normalized difference, they will mapping the subtle color change into the normalized difference map, and they can use CMM to extract rPPG signal from this kind of map directly. And another branch is that he used the current face frame to learn a attention map, for example, skin attention map. And after that, he attention back to the normalized difference range, so that it will filter out the background, undesired background change, so that they can focus on the facial color change. Another famous framework is proposed in ICCV 2019 is that also an end-to-end framework, but they consider the spatial-temporal information into the level design. They first design a spatial-temporal video enhancement network to even though your input video might be low quality, for example, very high compression rate or low face resolution, it doesn't matter. They will reconstruct the facial video with higher quality. The quality means that they may contain richer rPPG features. After that, they will design rPPG net to extract the rPPG feature directly and predict the rPPG signal. Here is a demo to show the original input, the enhancement, and the attention map and the prediction. As you can see, after the video enhancement, the rPPG net can extract more clear signal compared with the ground truth ECG signal. We also introduced the current data set for rPPG measurement. Especially, we mark that with their applications. In this data set, you can see in the early years, the data set usually the subject number is very small, and the video number, this by width, because the video is very short, we can it's unfair to compare with other video. But you can see the video number usually less than 1,000, and mostly these video are recorded in the lab environment with very less head motion or some other environment trend, for example, light changing. So it is easy to get high accuracy on this data set. But after that, there's some very challenging data set. For example, VIPR-HR proposed it have a very huge amount of video numbers and larger than 100 subject numbers. And there, you can see in this scenario, the head movement is very serious. If you use the traditional end-to-end method or traditional single process method, is very challenging to get a very accurate rPPG signals. And according to the applications, we summarize the rPPG application into this fourfold. The most important application is affective computing. After it extracts the rPPG signal, we can apply into expression recognition, stretch recognition, pattern recognition, or engagement measurement in educational activities, or deception detection, or monitoring the driver status. Besides that, rPPG can also apply in monitoring or attribute fibrillation detection, and someone also apply in some biometric security application, for example, face anti-screen or deepfake detection. And lastly, for example, for Microsoft, they already applied the rPPG technique into their AR glasses, for example, their HoloLens. So I think in the future, they will be, with the rPPG technique become more robust, there will be more interesting application will be applied in our industry. After that, I will introduce our paper, AutoHR, strong end-to-end baseline for remote heart rate measurement with neural searching. If you can, if we observe the rPPG development across the time dimension, we can see that from the 2080, the first end-to-end method proposed. After that, there will be some spatial-temporal version, and but still some challenges. For example, there's some complex illumination, how to select RI, and how to overcome the issue of the head movement, or according to the deep learning, right? How to decide the supervision signal for the neural parameter updating, and how to decide the neural architecture, right? This is so many problems for the especially end-to-end rPPG measurement. So we do some experiment and to find that, okay, existing end-to-end method, for example, PhysNet, DeepPhysi, i3D, they are all very famous spatial-temporal networks in rPPG measurement. They perform very poor on VIPR HR data set. Because you can see in this data set, we have serious head movement and different kind of illumination. Compared with the traditional single precision method, unsupervised, the end-to-end method only outperform them by a very slight margin, right? But compared with some non-end-to-end method, for example, this method, they usually use very strong pre-processing procedure before using the deep learning method. So after that, their representation is already very strong. So the head movement or other facts will influence this kind of method slightly. So and the next question is that end-to-end method generalize well in this challenge scenario. In this paper, we find three factors. One is the network architecture, one is the loss function, one is the data augmentation strategy. These three facts influence the robustness and the generalization ability of the end-to-end rPPG network heavily. So to overcome these three issues, so we in the network architecture side, we design two new elements. One is called temporal difference convolution. One is that we automatically search the optimal architecture for rPPG measurement. Another, according to the loss function design, previous work, they usually only consider the time domain frequency or frequency domain constraint to supervise a neural level to learn rPPG cues. In this work, we propose to hybrid loss to combine these two domains together. Another thing is domain augmentation strategy. As we can see, compare with the generate vision task, for example, object classification in ImageNet, they are very large scale training data, right? But in the rPPG task, the video is very small scale, and there are maybe label distribution. For example, the high heart rate, average heart rate usually have smaller samples than the low heart rate distribution. For example, after someone doing some exercise, their heart rate maybe will be very high. For example, average heart rate larger than 100 BPM, like that. But in current data set, there are very few this kind of sample. So they will cause a long tail distribution, which will force the network to learn most cues only on the easy sample, but negative this very hard sample. So according to this situation, we propose some spatial temporal cutout and the temporal upsampling and the downsampling strategy. The first introduced is the temporal difference convolution, which is inspired by the deep physics work. Because in the deep physics work, they calculate the normalized difference between two frames at the in the raw frames level, right? But we can imagine that in the raw frames level, because to the of the sensor noise, it's very challenging to estimate the color trends, facial color trends in the raw frames level. Usually, it will calculate a difference from the maybe sensor noise or some other undesired trend, but not the our desired rPPG color trends. So we want that, okay, maybe we can calculate this kind of difference in the feature level, right? So we can decide this difference mechanism into the convolution. So we propose the temporal difference convolution. In this convolution, you can see from that we consider the kernel equal to 3. In this case, we just consider current frame, maybe the previous one frame and the feature one frame, right? And for the current frame, we just calculate the spatial convolution. But for the adjacent frames, for example, t -1, t+1 frames, we will extend the current frames, current location intensity to the other two frames, and they will do the difference. So the different information you calculate in the across these two frames and these two frames. After that, we aggregate, we learn this convolution and aggregate all these three frames information. So the output will contain both the current spatial information and the adjacent difference information. If you use the equation to represent, we can represent it like this. This is the current frame, the 2D convolution, right? This is the the temporal difference convolution in the t-1 frame, and this theta, it controls the how the contribution of the temporal difference, and this is calculate the temporal convolution in the future frame. And a higher value of the theta means that, okay, we put more importance of the temporal difference information. And especially when the theta equals to 0, right? So this part is removed. So this will be a vanilla 3D convolution. And based on the temporal difference convolution, we design a new search space to search the optical architecture for the rPPG measurement. As you can see in the operation space, besides the traditional convolution, for example, the spatial temporal convolution, the spatial convolution, we also include our temporal difference convolution with two kinds of theta. For example, theta equal to 0.20, 0.1.0. So we assume that maybe with this huger search space, they can search more suitable architecture or operators for the rPPG measurement. And for the network space, we follow the similar network design as the PhysNet. So we use spatial convolution to aggregate the face feature first, and after that we use 4 blocks. Each block have 2 cells, and all these blocks may contain 2D convolution or 3D convolution or temporal different convolution, right? And after that, we use some shallow heads to recover the rPPG signal. For example, you can use some deconvolution or use some simple linear upsampling strategy. And inside the cell space, we use some 2 input nodes and 3 intermediate nodes and 1 output nodes to represent their node interaction. So our goal for the backbone search is that we search for these 3 intermediate nodes, and which node there will be some edge connected to it. Each edge also represent 1 operator. So our goal is that, okay, we search the operator and which edge should connect to the different nodes. So it will be a very huge search space. And we also consider, okay, the block, the cell will be shared, or the cell will be unshared, right? If the cell is shared, the search space will be smaller and it's easier to converge. And for the search optimization algorithm, we choose the very classical bi-level optimization. So we will separate the training set into 2 parts. One small training set treat as a validation set. And first, we will fix the architecture parameter. This is our goal, alpha we want to search, right? We fix it first and train the network parameters on the training set. And after that, we will fix the network parameters and update the architecture parameters on the validation set. And after the searching converge, the final architecture will be from setting the maximum probability of the operator for each node, and we also choose 2 incoming edge for different nodes. As after here we show our search cell in our AutoHR. You can see that in the formal nodes, it usually use some for example, some temporal convolution like 3 by 1 by 1 or 5 by 1 by 1 like this. But in the latter node, for example, this node 2, it usually adopt spatial convolution like large kernel spatial convolution like that. So we think maybe this finding can facilitate our future architecture design in this field. Besides that, we also consider the supervision in both time domain and frequency domain. In the time domain, we adopt the negative Pearson correlation loss to force the predict rPPG signal X maybe should be with a similar trend with the ground truth BVP signal Y. And we also consider the frequency domain. First, we will transfer the predict rPPG signal into the frequency domain using power spectrogram density. And after that, we will force the distribution of this of the PSD. The maximum frequency index will be as close as our ground truth heart rate as possible. So we will merge these 2 loss together, use a hyperparameter 0.2 for trade-offing. Besides the architecture and loss function, we also design two spatial-temporal data augmentation strategies. For example, here we consider the cutout, spatial-temporal cutout. The motivation is that we find that in some video, they usually with some occlusion, for example, some hand, they will cover their face, or some maybe mask they will wear in their face, or some head movement they will partial face losing in our face detect bounding box. So how to overcome this issue is that we randomly cut out, maybe for example 20% spatial size and 20% temporal length. For example, this blue tube, this red tube, or this green tube. So this will mimic the situation of our eye occlusion. Besides the spatial temporal cutout, we also consider the temporal upsampling and downsampling. For example, given a sequence in the second row, we can easily to generate actual samples with maybe higher or lower heart rate value. For example, if we sparse sampling the friends into this sequence, or we will we include the future friends into the current sequence, but with more higher frame rate, with lower frame rate. So we will corresponding our ground truth can be also calculated based on this sampling strategy. For example, if we have one more time sparser sampling rate, right? In this case, so if we giving input of 100 frames, so this 100 frames will contain more more second information. So in this case, we assume that maybe their heart rate will be larger than the original one. So we can use this strategy, maybe generate more high heart rate value samples for training. And for our experimental data set and evaluation metric, we focus on the most trending one, vipR-HR, and also one classical data set, malloc HCI. And we also do the cross-testing when training on the vipR-HR and the testing on the MNSE-HR. The evaluation metric is using SD, MAE, MSE, and the Pearson correlation coefficient. First, we show the ablation study of our method. The figure 8 shows how the loss function influence the performance. You can see if we only use the time domain-free constraint, the error rate, the MSE will be very high. Means that okay, they are hard to learn the maybe intrinsic rPPG features. If we use the frequency constraint, it will be easier to learn the periodic trend. But if we merge it together, we will get the better result than any one loss. We also give some operation about the temporal difference convolution. The Validant 3D convolution is that when the theta equal to 0, right? The MSE is acceptable, but using temporal difference convolution, we can see when the theta equal to 0.2 and 1, it will get better performance than the original 3D convolution. That's why we choose these two candidates into our operator space for architecture search. And for the figure C, we can find that if we, without architecture search, so the architecture is similar to the PhysNet, but we use the overall loss. Their intra-testing and the cross-testing result is not very satisfied. But if we use our architecture search with shared cells and with our temporal difference convolution in the operator space, the architecture especially they perform very good in the cross testing. You can see the origin color. And we also interested in, okay, if the search space without temporal different convolution, and or if the search space with not shared cell, but with independent variant cells. So the other result is not very competitive as this setting. So we use this setting for the further experiments. And for the data augmentation strategy, we also find that if we only use the spatial-temporal cutout, the performance will be dropped. It's very interesting. But if we combine the spatial-temporal cutout and the temporal upsampling and downsampling, the performance can be increased, can be improved sharply. Ablation study, we will compare with the performance with some state-of-art method in vipR dataset. We can see these three kinds of rows. This block means the unsupervised signal processing method. This block means the long end-to-end deep learning methods. The last block means the end-to-end deep learning method. It is clear to see that our AutoHR compared with other end-to-end method, we will get better performance. But it's still a gap between end-to-end learning method and the long end-to-end learning method, right? You can see these two methods can very easily beat all the end-to-end methods. So it's still maybe a further step to run how to improve the performance for end-to-end learning method. We also conduct experiment on the Mahalov HCI. The sample visualize some sample like this, and we can also find the similar observation is that the long end-to-end method can outperform the end-to-end method by a large margin. But our AutoHR is still better than the previous end-to-end method. When the testing on vipR and the testing on MSHR, it's interesting to find that our AutoHR, our generalization ability is better than the long end-to-end method. That means that the long end-to-end method, maybe they work very good in the inter-testing like these two datasets, but they are maybe overfitting in some domain. For example, there are different kind of environments. They are overfit, but it's hard to generate in other domain. For example, MNHR, SEHR. But our method, it seems our generalization ability better than this kind of method. This is interesting and very inspirable for the future design of the end-to-end method for rPPG measurement. Finally, we also give a visualization of the baseline PhysNet and our proposed AutoHR. You can see when the input with very large head motion, the PhysNet usually they will focus their feature response view. For example, you can see in this head nodding, right? Their feature we focus on the leg, but not the maybe facial tricks, and they might be undesired feature response. That's why they are not very good in the series head motion scenario. But for our AutoHR, it seems the feature response always focus on the facial region. For example, even though in this training case, most of the face the feature inside the face have been activated. And we also compare with the predict single in this head movement scenario. We can see in this short period, it corresponding to this input. Okay, we can see that the baseline PhysNet will predict a very noisy RPG signal in this period. But compare with it, our AutoHR with maybe acceptable RPG prediction, even though with a serious head movement. Conclusion is that in this letter, we find three important factors. Network architecture, loss function, and data augmentation influence the 3D-CM-based end-to-end framework heavily. And we propose several solutions to decide the AutoHR, and it generates well in less constrained scenarios. And our work had already been a solid baseline in this field. It already had 50 citations. It means that many work are inspired or followed by our AutoHR. And we hope also we can, our design architecture and the loss function and the augmentation strategies will inspire the RPG community and maybe help their future research. Okay, this is my presentation. Thank you.
Thanks a lot, Zitong.
Thank you.
Are there any questions?